Welcome back to our study of the derivative in as we try to complete here our first quarter of calculus. The last topic we're going to deal with this quarter is one referred to as a linear approximation, and I want to show you today that this is nothing new. This is merely an interpretation of what you know. That's going to be the case in a lot of topics in calculus, and by the time we get into the what I call the regular season, when we're reviewing everything we learned and preparing for the test, you'll see I'm going to ask you to calculate slope 50 different ways. And once you recognize that, you'll see you can read these problems and work them with much greater ease. But anyway, in this particular, we call the topic is linear approximation. And what I have drawn here, I have this function. I have this curvy function here in general, and what I've done before is I might ask you, well, find the tangent line at the point A, right, at x equal to A. Like this might be A, and this is on my x-axis, right? And the red line is then a tangent line. And it's going to be a function of x. And notice, as you get closer and closer to A, the red line is right on. At A, the red line is right on the function. As you get farther and farther from A, you see, depending on the curve, the red line starts to deviate more and more. Out here, you see the difference is quite a lot. Out here, the difference between the red line and the function is quite a lot. But in here, as you get close to this point here, the straight line, or the linear approximation, is pretty good. Linear approximations are very useful because they're simple to compute. Computers can do them well. And if you did a successive linear approximation, you get a pretty good estimate of any kind of curve. So anyway, let's try to figure this out. And as I told you, this is nothing more than a tangent line. So let's write down what our tangent line equation is. And again, let's see what's going on here. Let me get my pen back. Tangent line. So we'd use a point slope form of the line where I would say what? Well, what's the slope of the red line? Well, the slope of the red line is going to be the derivative of the function. Where? Well, the derivative of the function at x equal to A. That is going to be the slope of the line, right? So I put my slope on the left. Now I need to know, well, what's the point? What point is on the line? Okay, well, A, here's my point. In general, it's A, f of A. So if I wanted to pick any arbitrary point out here, right, any arbitrary point on the line, x, y, I could then write, well, the slope of this should be the change between these two. And you'd say, well, the change in y is just y minus the point I know that's on the line, f of A, right? Or x minus A. Okay, so this is my form of the point slope form of the line. I'm going to modify this, multiply both sides by x minus A as I did before. I like to put my y's on the left, so I'm going to say y minus f of A. Right, remember where this comes from? And then multiply both sides by x minus A, both sides by x minus A. So I get y minus f of A is equal to f prime of A times x minus A. Okay, I can do a little bit more with that. Get this thing out of the way here. I can do a little more of that with this equation. And I'm going to get my pen back. Start green here. I could say, well, y, I'm just going to push this to the other side. I'm going to say y is going to be f of A minus f prime of A times x minus A. That indeed, this then, that's what we would call our tangent line. remember, it's a tangent line at x equal to a. And then we also might say, well, that's equal to, let's just say that's a line. Okay? It's a function of x, right? A is a constant. This is a constant. This is going to be a slope. This is going to be a number. You give me an x, though. This is the independent variable, and there's the dependent variable. Okay? Let's look at this a little bit. Well, what's L? What is L? And so this is a function. What's L at A? L at the center point is just going to be f of A minus f prime of A times A minus A. Okay, that's 0. So L of A is the function of A. And that just says, well, yeah, right at the center, there is no error at all. Okay? So this, though, let me just write this down. This is the linear approximation. Again, maybe you can skip through this video quickly to the example. What is a linear approximation? It's a tangent line. It's an interpretation of a tangent line. See what we got here next. Just to write this down, make it a little formal definition. L of this is what I just wrote down, is the linear approximation, linearization, or the linear approximation. Linearization, linear approximation of the function at x equal to a. There's my drawing again. Notice that is a standard linear approximation. Notice the approximately equal sign. Approximately equal. At the center point, they're exactly equal. At a, they're exactly equal. As you get away from a, it depends on the function how close they are. Okay? Now, approximations have errors. Approximations have errors, okay? Good approximations. I mean, approximations are not boring things. I mean, approximations are why all of a sudden big ideas become cost-effective enough for it to change the world. So you want an approximation that's good, that doesn't cost much, but that it maintains the quality of the original function. But approximations have errors. Can you find the error? Okay, so we need to work a problem. Okay, we need to work a problem. Okay, here's an example from your textbook, a problem on linear approximation. They give you this function, square root of 1 minus x. They tell you to find the approximation at a, or at centered at a equal to 0. Use it to approximate the numbers 0.9 and 0.99. Okay, let's see if we figure out what this question is asking. It's a simple question once you figure out what it's asking. And they tell you here at the end they'd like you to illustrate by graph. I'd like to get a picture to start with. You know, I'm big on pictures. See if I can graph this. I guess they indicate you can use your graphing calculator. Let's see if this is like saying y is equal to the square root of 1 minus x, or what? If I square that, I'd get y squared is equal to 1 minus x, x equal to 1 minus. I'm just trying to get a feeling for what this thing is. This is a parabola opening to the left, and it looks like it starts at 1 here. Notice y is always positive in this case, so this function looks like this. Does this make sense? At x equal to 1, right, 1 is 0, and at 0, it should be 1. Okay, what is this function here? This is f of x. Okay, what do they want to know? Well, they want me to get this tangent line. So when you picture this thing, see if I can draw a good tangent line here. And all right, and what do they want to know? They want me to find this tangent line. I'll call L of x. And then they'd like me to use it to approximate the numbers 0.9 and 0.99. Okay, so let's go. Let's find the tangent line. Well, we need to know, first of all, we need to know f prime of x. F prime of x, well, remember, I like to write this thing to the 1/2 power. Use the chain rule. I say 1/2 comes down, 1 minus x. I power this thing down. That's now to the minus 1/2. Then I've got, what's the derivative of the inside? Ooh, the derivative of the inside is -1. Don't forget that. Common mistake. So I could write this as -1, and I could put the 2 times the square root of 1 minus x. Another way to write this, okay? This is the derivative of that function. Got to be good at taking derivatives. Now, where do they want this? Well, I want this thing, I'm interested in this at x equal to 0, right? It says a equal to 0, centered. I want my tangent line centered right there. So if I put in x equal to 0, what do I get? I get -1 over 2 times the square root of 1, just -1/2. Okay, so what's my tangent line? Well, -1/2 is equal to, what's my point on the line? My point on the line is 0, 1, so it's going to be y minus 1, x minus 0. And I rewrite that. I say that's y minus 1 is equal to -1/2 x. And I could say y then is equal to simply -1/2 x plus 1. This might be what I call L of x. Okay? There is my linear approximation. So I did that. I found the linear approximation. That is my red line here. Now they want me to approximate what 0.9 is. Well, now I got to figure out 0.9 means what? I want the square root of 0.9. Well, what's x equal to at 0.9? Okay, 0.9 is equal to 1 minus x. So that means at x equal to 0.1, right? Yeah. So what they really asked here is they're going to say the square root of 0.9 is equal to, it's really equal to the function at 0.9, the true function. But I'm going to approximate that with my line at 0.1, which is just going to be equal to -1/2 of 0.1 plus 1. And that's going to be, this is 0.05. This looks like it's 0.95. Okay? Similarly, the square root of 0.99, well, that is equal to exactly the function at 0.01. Okay? If I 0.1 minus 0.01 will be 0.99. That's going to be equal to -1/2 times 0.01. Oops. Which is, let me not confuse you. Eraser. Pen, see how quick I can get here. That's just the line. Notice the squiggly equal sign. These are not equal. This is an approximation. But that line is equal to -1/2 times 0.01 plus 1. I'm just plugging in. I'm merely plugging into that line. And this is going to be 0.995. Okay? This is going to be 0.95. All right, so if I went up here and plotted these things and I took the time to do this, I'd say, well, my line at 0.1, I just found 2 points on the line, one here and one there. And you can see the black dot is not on the blue line. You might say, okay, I'm over 15 minutes. We'll see if it lets me upload it. But here, I want to just finish this. What's the true value? This 0.95 is approximately equal to the function of 0.1, which is, what's the square root of 0.9? Second square root of 0.9 in my calculator. I got this to be 0.9487. So 0.95 is pretty close to 0.9487. How about this down here? This, what's the square root? This is approximately equal to the square root of 0.99. And what's that? Let's see, 0.99. This is equal to 0.99499. 0.9499499. So it's very close, and you can see as you get closer to the center point, which is 0, the approximation gets better and better. As you get farther away, the approximation gets worse. I hope this didn't go too long. See you soon.